Physical science, we're moving on in Module 14 to the Doppler effect. This is a very short video. The only thing we're covering in this segment will be the Doppler effect. So what is the Doppler effect? A Doppler effect is an increase or a decrease in the frequency of sound, light, or other waves as the source and observer move toward or away from each other. The effect causes a sudden change in pitch noticeable in a passing siren as well as the redshift seen by astronomers. So it also has something to do with light, which we're not going to get into yet. The Doppler effect was named after Austrian physicist Christian Doppler. In your text, experiment 14.4 demonstrates the Doppler effect. The idea is to stand still and have a car come towards you slowly, honking its horn, and then pass you. As the car travels towards you, the pitch of the horn honking is higher than when the car passes you and starts traveling away. This motion demonstrates that as the frequency of the sound waves changes, the pitch of the sound changes and the sound waves change also. When sounds are heard from a stationary object, and you are also stationary, the waves produced hit your ear at the same frequency as when they left the sound producing the object. So when you're sitting in a car honking your horn, you're actually hearing that horn's true frequency. But when a car is honking its horn and it's coming towards you or moving away from you, the compressions and rarefactions of the waves get bunched up in front of the object and stretched out behind the object. That's when the pitch changes. In your text was this picture. I'm going to zoom in a little. And it shows a car, and here you are standing. The horn from a car produces sound waves at a constant frequency. But when the car moves, the horn emits those waves as the car travels. So here's the waves actually emanating from the car. So consequently, after it has emitted one wave, it moves forward to emit the next. And this keeps going on and on. This causes the waves to be bunched up in front of the car when it's coming towards you and stretched out behind the car when it's going away from you. Since the sound waves get bunched up in front of the car, the wavelength is shorter. You can actually see this visually in the picture. So the frequency is higher. Remember, shorter waves, higher frequency. If the car's heading towards you, then you will hear a pitch that is higher than the pitch the horn actually produces. When the car passes you, the sound waves that reach your ear are the ones traveling behind the car. They're stretched out, which gives them a larger wavelength and thus a lower frequency. So larger wavelength, lower frequency. This results in a pitch that's suddenly lower than the pitch from the horn. So in your notes, this is what you should have. When an object is heading towards you, then you will hear a pitch that is higher. Or let's say it this way. The wavelength coming towards you is shorter, so the frequency is higher and the pitch will be higher. The wavelength of the car going past you or traveling past you will be stretched out. That makes a larger wavelength, thus a lower frequency and a lower pitch. So those are the correlations that you need to have. And that's it for this very short video. We'll be moving on to our last video in the series, 11F. And if you have any questions, be sure to let me know.